Hello, and welcome back to Chapter 11, Mathematics and the Arts. Today, we're going to talk about proportion and the golden ratio. I know, we talked about proportion, we talked about perspective last time, didn't we? Now let's talk about proportions. Here we go. Geometry has two great treasures. One is the theorem of Pythagoras, the other the division of a line into extreme and mean ratio. The first we may compare to gold. The second we may name a precious jewel. Johannes Kepler, incredible astronomer, mathematician, astronomer. He did some great work. And he did some great work in mathematics as well. And really, what he's saying is that just as well as we know the Pythagorean theorem, x squared plus y squared equals r squared, is what comes naturally to me, but you actually know it as a squared plus b squared equals c squared. The Pythagorean theorem, right? Everybody knows that. That's like gold in terms of math. Well, what we're about to talk to right now, this golden proportion, it's more of a precious jewel. Let's take a look. It's called the golden ratio. The ratio of the length of the longer piece to the length of the short piece is the same as the ratio of the length of the entire line just to the long piece. So long piece is to short, as the whole thing is to the long piece. Nice little proportion. And this proportion, the way we set it up in this ratio, right? As we look at the fractional relationship between these two, for the ratio, right? That's how we compare things. The ratio of capital L over little l. For any line segment divided into two pieces according to this golden ratio, phi, the ratio of the long piece to the short piece is approximately 8/5. 8/5, all right. But this is what it actually is. 1 plus the square root of 5 over 2. That's the exact value. This is our approximate. And I'll be honest, we will rarely use the 8/5 idea. Yeah, cool, it's close, whatever. But these are the values of phi as we need to know them. Notice phi on your keyboard has two different representations. They are exactly the same character. I don't know, we have too many ways of representing the same letter. Let's look at the Parthenon and its proportions. The golden rectangle is a rectangle whose long side is phi times as long as its short side. So whatever the height of the Parthenon is, and it used to go up here actually, it was higher. You could see in the rubble how it has come down. The Parthenon was higher. If we take that height and we multiply by phi, approximately 1.618, we'll get the length of the Parthenon. It's crazy, it's cool, and it's true. A lot of things built throughout the ages have had these golden proportions built in. So let's look at some household items, right? A standard sheet of paper is 8.5 by 11. An 8 by 10 picture frame, right? 8 by 10 frame looks great up on the wall. It's 8 inches by 10 inches. And a high def television, it always has a 16:9 ratio, right? It has the letterbox version for maximizing the output of the visuals of the movie or whatever you're watching. Well, wow, that's interesting. I hope the rest of it comes. The ratio of the sides of a standard sheet of paper, right? The big side divided by the small side is 1.29. And we're comparing it to 1.618. Well, there we go. There's more of it, I guess. I guess. That's weird. Let's erase all the ink on this slide and go back to the pen. All right. The ratio of the sides of a standard sheet of paper is 11 over 8.5, which is about 1.29, 20% less than the golden ratio. So we're comparing 1.29 is what percentage of 1.618. So I'm going to divide and 20% less. Okay. I meant that the other way around. 1.618 is what percent? Oh my goodness. Forget I said that. Because now in my mind, I can't put any of it right. I want to compare 1.29 to 1.618. How much short is it? And I want a percentage, so I'm going to use a ratio to compare. My goodness. Okay, here we go. The ratio of the sides of a standard picture frame is, right, an 8 by 10, biggest to smallest, 10 to 8, 1.25. So that's even more off from the golden ratio than the standard sheet of paper. But our TV, right, 16/9, 1.78. It's only a little bit more than the actual golden ratio. And to have integer values in order to give us this, of the three objects, the high-def television is definitely closest to being a golden rectangle. And maybe that's why we stare at it so much. Now, this golden rectangle can be broken into a square, right? So this whole thing is a golden rectangle, and then we take out this square. And what's left here is now a golden rectangle. And from that golden rectangle, we could take out a square. And what's left is a golden rectangle. And from that golden rectangle, we could take out the square, and what's left is a golden rectangle. And we could take out that square, and what's left is a golden rectangle. And we could take out that square, and what's left is a golden rectangle. And we could take out that square, and what's left is a golden rectangle. And this process continues forever. And if you connect all the corners of these squares, they keep going around, you'll get what's called the logarithmic spiral, or a golden spiral. And the Nautilus shell is a great real-life example of what that is. These actually are for buoyancy. It builds onto its house as it gets bigger. It needs more buoyancy as it gets older. But it looks a lot like a logarithmic spiral. All right, let's talk about Fibonacci. Fibonacci lived in the 1400s, early 1500s. I know for sure in the 1400s. So he was around the time of Da Vinci, kind of in the time of the reawakening after the Dark Ages, and math was, Fibonacci might have been in the 1300s. He might have been the lone shining light of the Middle Ages. But he came up with this sequence based on rabbits, and we'll see this in the next slide. But basically, we start with, I can't find my cursor. Nope. All right, my cursor's not here. There we go. I'm not the pen. Here we go. We start with 1 and 1. 1 plus 1 is 2. 1 plus 2 is 3. 2 plus 3 is 5. 3 plus 5 is 8. 5 plus 8 is 13. 8 plus 13 is 21. You start with 1 and 1. You add the two numbers to get the next. Add the last two to get the next, and so on. We say that the next Fibonacci number is the current Fibonacci plus the one behind it. All right. The next one is the current Fibonacci plus one behind it. And we can see this in rabbits. All right. So you have a pair of baby rabbits, and it takes a month for them to become an adult. So we have one set of rabbits, and then we have one set of rabbits. After 1 month, and they've matured, now they've given birth to a set of rabbits, and they're still here, right? So we have those two pairs now, the babies and the originals. Well, every month, the originals are going to have more babies now that they've matured. But these new babies have to mature a month before they can have babies. So it's 1, 1, 2. Here we have, oh, look, they're right there, 3, 5, 8. And we can see the different pairs based on 1 month of maturing, and then they can reproduce. 1 month maturing. And supposedly, rabbits was the genesis of the Fibonacci sequence. I kind of doubt that, but it's a great example. It's a great way of motivating it today. If we look at various Fibonacci numbers, right? I'm gonna write down some. Yeah, I should talk while I'm doing this. It's a video, not just a... And so on. Okay, so I'm going to take ratios. 1 divided by 1, that's kind of boring. So we start here with 2 divided by 1. 3 divided by 2. 5 divided by 3. 8 divided by 5. And we just see what these decimals are. Notice we're up here at 2. And let's put this at 1. And this is at 2. So we're up at here at 2. and then 1.5, and then 1.67 and 1.60. And then we just start kind of dialing in 1.6, 1.625, jumps up, jumps back down, jumps up, jumps back down, 1.617, 1.618, 17, 18. Oh, now this 1.6180 is getting consistent. Notice the further and further we go up with Fibonacci numbers, and we keep doing the exact same ratio, 1 divided by the previous, we end up settling on this same number, phi. The same number phi comes up, and it's the ratio, the limit of the ratio of consecutive Fibonacci numbers. It's just really cool things happen to come around again and again and show up in our architecture, in our number patterns, and everywhere we look. That's it for proportion and the golden rectangle. Thank you very much for listening.